So for this video, we'll discuss topological sorting. Topological sorting is based on directed graphs. So far, we've talked about bidirectional graphs, where if you can get from one point to another, you can go back. So if you can go from A to B, you can go back. For topological sorting, we use directed graphs, and they use one-way rather than bidirectional links. And we show this by putting an arrowhead at one end of our edge. In the graph below, you can go from A to B, and you'll notice that there's a little arrowhead by the B. So we go from A to B. You can also go from B to C. Note the little arrowhead near the C only. You can't go from B to A. You can't go from C to B. You just go in the direction of the arrow. If we wanted to represent this in an adjacency matrix, for each edge, we'll put only a single one into the 2D array. Previously, with the bidirectional, for each edge, we'd put two different ones in the array, and we would get a mirror image across the diagonal. But here, that doesn't happen. So since we can go from A to B, we put a 1 in row A, column B. Since we can go from B to C, we put a 1 in row B, column C. But you'll notice we're not putting ones indicating the other direction because these are one way. So topological sorting. This is used when items or events must be in a particular order depending on previous items or events. Lots of examples. If we're building a car, we might want to put the handle on a door before we put the door on the car. Cars have thousands of parts, so while there are a number of different orders that will work, there are some orders that are definitely best to avoid, and we can plan for that. If we might assume that we read a book before we write a report on it and write a report before we present it, although I know some of you have done those in different orders. But that's what we typically assume. And there are software programs such as Microsoft Project, they keep track of which events have to occur before other events. Back about the time I was born, there were some large complex projects starting for the Cold War. One of them was the Polaris project, which involved being able to launch intercontinental ballistic missiles from nuclear submarines. Building a nuclear submarine was complex. Building these missiles was complex. Getting them to work together was complex. And so they felt a need to track all of this out in advance. In particular, they were interested, most project software is interested in when the order doesn't matter, when you can do something in parallel. So most of the development of the submarine can be done at the same time as most of the development for the missile. But eventually you get to a point where you want to test the missile from the submarine. And to do that, you need to have both a completed missile and you need to have a completed submarine. And so project software would keep track of that. They first came up with this, they called it a PERT chart, and I forget what the acronym PERT stands for. When they first did this for Polaris, they used sheets of paper that ran from floor to ceiling all the way around a room that was about the size of a gymnasium, and they started drawing on it with pencils and pens. And occasionally they'd realize that they had a problem and they would have to revamp things a little bit, and then they would cut a piece of paper and tape it over the top of the first sheet and write on top of it. So doing this in software definitely has some advantages. It means that we can use the software to spot things like the shortest path through the projects, taking advantage of the overlap, what we call the critical path, which is the path that you can't shorten because you can't move one thing before another. And project software will do all that sort of thing. So given a list of events and their dependencies, we want to put them in a usable order. You can say, well, this lets you draw them in a usable order. That's great. But we would like some ways to know whether we've gotten an order that will work, some things like that. And that brings us to topological sorting. So LaFleur uses the example of prerequisite courses for college graduation, and we will too, but I'll use the Covenant Core for our example. There's some other places we could use this. For instance, we could look at the CS programs to become a CS major required for graduation, but I'll use the Covenant Core for our example. So I went to the catalog, and these are the core courses that are required. You're familiar with these. And these are the dependency. Let's just take the first one. Bible 277, that's Doctrine 1, and it requires that you do Bible 111, which is Old Testament, Bible 142, New Testament, before you do Doctrine 1. And there are a number of other prerequisites scattered through here. So this is the list of the dependencies. So we can draw these as a graph and look something like this. You see I've added a sort of a dummy node called core requirements completed. And so core requirements are not completed until all of these directed graphs are taken care of. So far, so good. So how do we actually have an algorithm that'll go through this? And visually, you can probably get it right. It's not that complicated once you get laid out like this. But we use topological sorting. And the rules are rule 1, find a vertex that has no successors. Now, what's a successor? It's a node that's not a prerequisite for anything. And the diagram we just looked at, only the final core requirements completed has no successors. So rule 2 is once we find that vertex that has no successor, we delete it from the graph and we insert its label at the beginning of a list. We repeat rules 1 and 2 until there are no more nodes in the graph, and then the list gives an order of the steps that will work. Now, this is not unique. There may be many different orders of steps that will work for a given graph, and we'll see an example of that pretty quickly. So if we go back and take our previous graph, this one, and we remove that core requirements completed, what we get is this. And you'll notice down at the bottom here, I've started my list and I've said core completed. Okay, so we have these different pieces. You'll notice they're no longer all connected. And now we simply have to pick something that doesn't have a successor. And there are lots of candidates here. Bible 277, Bible 278, core 325, core 337. There are lots of possibilities. We could pick any one of these. For somewhat arbitrary reasons, I'm going to pick the one with the longest path. That's often a good rule of thumb. And so I'm going to get rid of core 325 next. And so we take 325 off of the graph and we put it on the list. And so now we know that we have to do core 325 before we get to core completed. And now I'm once again going to go back to the longest list. That gives me history 325. So I take it off the graph, put it on the list. And now I have a number of possibilities. And I pick core 337. Actually, that's not quite following my rule of logic about the one with the longest path, but this will work. This will be fine. There's not a unique order. And so now I have lots of things that have one prerequisite, and I'm just going to go from the top down, and I'll pull off doctrine 1, and now I'll pull off doctrine 2, and now I'll pull off chow 1, and I'll pull off chow 2. I'll pull off Christ and culture, and I'll pull off P152. And now I have a bunch of things left, none of which have prerequisites, so I could pick them in any order, but I'll just go top to bottom again and grab Old Testament and New Testament and English composition and Christian mind and P151. And so there's our final list. And this list is in an order that will work. You won't try to take anything before you're allowed to. But of course, as we noted, there are a number of orders that we could have taken these off in. Okay, one thing to look out for are cycles. You cannot do a topological sort of a graph with a cycle. Here's a little graph that has a cycle in it. That is to say that there's nothing that has no successor. Everything is a prerequisite for something else. Everything has to be done before something else. And so there is no point you can finish at or start at and be correct. A cycle would indicate that you have to do a particular thing before you can do that thing, which makes no sense. Okay? A graph with no cycles is actually a tree. It's the definition of a tree. So in a sense, we could say that you can't do topological sorts on a graph. You can only do them on a tree. But we normally think of these sort of sprawling trees, such as the one we did for our prerequisites, as having more to do with graphs than having to do with trees. By the way, compilers use topological sorting to see if you've declared everything that you use before you use it. And if they find a cycle, they have to punt. So maybe I have a class with a node. I have a node class, and I have a program that uses it, and I have something in that, some data type in that class that's a data element of a node. Which one comes first? Well, we get a cycle, and often we resolve that by saying this is an error. We can't do anything with this. We can also have something called a forward declaration that just says, yes, we will declare this, trust me, go ahead and start later. LaFour has the code to do topological sorting starting on page 654 if you want to see it in gory detail in Java. We won't particularly need that for the course, but it's there if you're curious. I'll just mention connectivity in directed graphs. Here's a little directed graph. And in a bidirectional graph like we've been using, you can always start anywhere you want and get to everything by using either a depth first search or a breadth first search. And when we did our example, we started at sort of an obvious place of a node A. You recall that in an earlier lecture. But you could have started anywhere on those and it would have worked. Here in the directed graph, where we can get to depends on where we start. So if we start at D, for example, there's no way to get to B. If we start at C, there's nowhere we can get to any place. So the order, the starting point becomes important. Well, that's what we have to say about topological sorting.